lesson, we are going to explore how to draw and how to interpret potential energy diagrams which show the change in potential energy as a reaction proceeds from start to finish, right? So in a chemical reaction, it always starts with the reactants, and the reactants have an energy that we're going to call H sub reactants, or H sub R, right? So these are the symbols that we're going to use to refer to the energy that is found in those reactants. We start with the reactants with a certain amount of energy that we label with the symbol H sub R, H standing for heat energy. It ends with products which have a certain amount of energy stored in their bonds, and we refer to that as the heat energy of the products. But there's something that happens in between, right? It turns out that when you have a reaction that happens, for example, right, a match will burn, and it'll burn exothermically, but not until you give it some activation energy, right? So we're going to give it some activation energy. And then once we give it that activation energy, this reaction is just proceeding on its own. Okay. So we have to add what is called activation energy. And in that moment of striking, a temporary activated complex is formed, and we refer to the energy of that activated complex as H sub AC for short, right? So we have these symbols that represent the energy of the reactants, the activation energy that we have to give to the reactants. We have the energy of the activated complex, which is this temporary structure when the reactants are in the middle of rearranging to becoming the products. And then we have products, which we symbolize their energy with H sub P. So if we were to take these terms and put them into a chemical equation form, we would see H sub R plus activation energy, which turns into this temporary activated complex, and then that in turn will form the products. So the question is the reaction endothermic or exothermic? But that really depends on, it depends on what the energy of the reactants is compared to the energy of the products. So if we kind of take a look at a very generic graph where we have time on the x-axis and we have potential energy on the y-axis, right? If we start with the reactants having a certain potential energy here, let's say the potential energy of the reactant starts out at 100, and this would be in kilojoules. If the reactants start out with 100 kilojoules, but then over time they turn into products, and those products have an energy of, let's say, 30 kilojoules. Okay. Reactants starting in time at 100 kilojoules, and over time, they turn into products with an energy of 30 kilojoules. Okay? So in this case, the reactants have a higher energy than the products, and we would say that this reaction is exothermic. Okay? We symbolize that with a negative delta H, and that negative delta H on this graph is right here. This is a negative delta H from this point down, right? This section right here is a negative delta H. Energy has to be released as the reactants turn into products. So if we think about this, right, we said the reactants starting at 100 kilojoules, the products ending at 30 kilojoules. We're going to have to add activation energy to that, which is not shown in this graph. And it's going to turn into this temporary activated complex. Again, these are not shown in this graph. But what we do know is that this is a negative delta H at negative 70. It's a negative 70 kilojoules. I'm going to rewrite that because that's just messy. Okay. So the negative sign means that energy is released, and the 70 comes from the subtraction of the difference between the 100 and the 30. Now, if the reactants have less energy than the products, let's think about this graphically, right? So we have the reactant starting low and the products starting higher. We say that that reaction is endothermic, and we have a positive delta H. So let's say here that the reactants are now starting at 30 kilojoules, and the products end up at 100 kilojoules. What we have here is a positive delta H, a positive 70 kilojoules, compared up here to a negative 70 kilojoules, right? So in this case, starting at 30, ending at 100, the delta H is a positive 70 kilojoules, right? But we haven't really talked about what these pieces are, so that's what we're going to take a look at next. The biggest thing I want you to recognize at this point is an exothermic reaction has reactants starting high and products going low. An endothermic reaction has reactants starting low and the products end up high. Okay, so the symbols we're going to use, right, let's make sure we have these symbols figured out. H sub R is the heat energy that is stored in the reactants. H sub P is the heat energy stored in the bonds of the products. H sub AC is the heat energy of the activated complex, that temporary structure that's sort of somewhere in between reactants and products, but neither reactants nor products. And the activation energy is symbolized by AE. And what this is the energy added to the reactants to get the reaction started. Okay, so let's create and analyze an exothermic potential energy graph or potential energy diagram. We're starting with exothermic, but I shouldn't have had to tell you that because we can figure out just by looking at this reaction. We've got reactants X plus Y turning into product K plus 40 kilojoules, right? The fact that the energy term is on the product side tells you that this is exothermic. So right away, we know here what the delta H is. The change in the energy from reactants to products is the energy term in the equation. And because it's exothermic, it's a negative, we report it as a negative number as 40 kilojoules. Okay. All right, now we're taking a look. We're given a piece of information that the heat of the reactants are 110 kilojoules, and we're given that the activation energy is 45 kilojoules. So let's see what we're going to do with that. We're going to have to figure out the energy of the activated complex, and we're going to have to figure out the energy of the products. So down here on this potential energy graph, we've got potential energy on the Y, we've got time progressing on the X, and then there's 3 dotted lines. We're going to ignore the top line for the moment, and we're going to use these 2 lines to represent the energy of the reactants and the products. Now, because this is exothermic, right? Exothermic, basically, we know that we're going to start high and end low. So that means, again, we're going to come back to this top line. Only on these bottom 2 are we're going to put a plateau here to start. Those are going to be our reactants, and then over time, time's going to happen, the reaction's going to happen, we're going to put our products over here. In this equation, our reactants are X plus Y, and our products are just K. Okay. Now, we know that the energy of the reactants combined is 110 kilojoules. We also know that delta H is negative 40. So from the reactants are going to lose, right? They're going to lose, this is the negative 40 kilojoules, that's the delta H, which means that the energy of the products has to be 100 minus 40 is going to be 70 kilojoules, right? So we just figured out what the energy of the products is It is 70 kilojoules because we knew the reactants and we know what the change in the energy was going to be. Okay, so what we now need to do is to recognize that there's something else we need to figure out. The activation energy, which remember is the energy added to the reactants to get the reaction started. We're going to add 45 kilojoules to the reactants, right? So here's where we have the reactants. We have to add energy to that. We're going to draw this graphically before we do the numbers. From the reactant energy, we're going to go up. We're going to draw the graph up to this line. And then we are going to bring it down until it meets up with the products. The energy that we had to add from wherever the reactants are up to the peak, and that's supposed to be a straight line. This is our activation energy, which was told to us is 45 kilojoules. Right, 45 kilojoules. Which means that if we add 45 to 110, we're going to get 155 kilojoules. That represents the activated complex, right? That's like sort of the intermediate. It's not the intermediate like jumble of atoms as they are in the process of rearranging from reactants into products. They're at this high energy state called the activated complex. So the energy, the heat energy of the activated complex is whatever the reactant energy is plus the activation energy, and that brings us to 155. So this is how you can interpret a potential energy diagram for an exothermic reaction where reactants start high and products end low. Now let's see what happens when we take that exothermic potential energy diagram and we add a catalyst. Okay, now remember a catalyst is speeds up a reaction, and it doesn't really, it's not part of the chemical reaction. It doesn't really get consumed or used up. It's able to be used over and over again. And the way that it does it is that it lowers the activation energy. Okay, and what that means, the result, is that you get to the product sooner. What won't change is the energy of the reactants or the energy of the products. But instead of the activation energy, right, so this right here is the activation energy of the uncatalyzed reaction. But if we want to add a catalyst, what will happen through a series of changing up the reaction mechanism path, you'll start at the reactant's energy level, and you will make the peak lower, and it will start heading towards the products sooner, right? So there's this right here is the activation energy of this arrow right here is the activation energy of the catalyzed reaction. And two things happened here. It lowered the activation energy and it got to the product sooner in time. What does this graph look like if we add an inhibitor? An inhibitor is going to slow down a reaction. It will do so by increasing the activation energy, and the result is that you get to the product later. So what does that look like? Well, right now we have this blue arrow, which is the energy added to the reactants, to get to the activated complex. That's the activation energy of the uncatalyzed reaction. But if we add an inhibitor, we're going to start at the reactants, we're going to end at the products, but we're going to take that peak is going to go higher, and it's going to be shifted to the right so that it gets to the product energy later. And so now this red arrow represents the activation energy of the catalyzed, or of the inhibited reaction. Okay, so that's the effect of a catalyst or an inhibitor on an exothermic reaction. Let's go ahead and create a potential energy diagram for an endothermic reaction. Now, I didn't really have to tell you that this was an endothermic reaction because this energy term is on the left side of the arrow, right? So that right there tells you that the delta H is a positive number, and it is positive 80 kilojoules. Okay. So we know something just by that energy term. We know the delta H is a positive number, and we know that that means that we have to add 80 kilojoules to get from the reactants to the products. All right, we are told that the energy of the reactants is 70 kilojoules. A and B is our reactants. C is our product. We are told that the activation energy is 120 kilojoules. Remember, this is the energy that needs to be added to the reactants. And we're going to try to sketch it onto this graph. Now, we have 3 lines here. We're not going to use the top line at first. We're always going to start with the bottom 2 lines. And this time we have to decide, are our reactants going to start low and our products end high, or are we going to start with our reactants high and our products start low? So let's think about that. If it's endothermic, energy is absorbed, we have to start low and end high. So starting earlier in time, that represents the energy of our reactants. On the second line, we're going to make a line that represents the energy of our products. Okay, so that represents our endothermic reaction, that basic relative position. We know that the energy of our reactants is 70 kilojoules. Okay. We know that our delta H, which is the energy between the reactants and the products, is a plus 80. So the difference from the reactants up to the products is a plus 80 kilojoules. That's our delta H. So that means we know that this amount of energy is 150 kilojoules. Right? We took 70, we added the 80, we got to 150. So we know that the energy of our products is 150 kilojoules. Now what we have to do is figure out where what the effect of the activation energy is. We know we're being told that we have to add 120 kilojoules to our reactants. So our reactants start at 70. We need to add 120 to that. That's where our activated complex is going to be there. So 120 up from the 70 we started with is 190. Of course, this is not to scale. Don't worry about that. And that means we're going to go from our reactants, we're going to go up all the way up to that difference right there, which is the activation energy, and then we're going to bring it down to where our products are. Right? So this line right here represents the activation energy, which we said was 120 kilojoules. The energy we have to add to the reactants to get to that activated complex right there. That is the temporary activated complex. Okay, so that means we know the energy of the activated complex to be 190 kilojoules. All right, so what then is the effect of a catalyst on an endothermic reaction? The catalyst, right now, if we go from here, from the catalyst, we start at the reactants, we end at the products, but a catalyst will speed up a reaction, it's going to lower the activation energy, and it's going to get to the product sooner. Okay, so it looks something like that. An inhibitor starts at the reactants, ends at the products, but the hump is going to go higher, and it's going to end up at the products later. So here's our reactants, here's our products. That's what it looks like with an inhibitor. Not so much, don't worry so much about how much higher you go or how much lower you go. It's just a relative thing to look at right now. All right, let's take a look at sort of an unlabeled diagram, and we have to attach the labels to it. So first things first, we have two graphs here. First thing to decide, is it endothermic or is it exothermic, right? So let's start by recognizing this is where our reactants are, this is where our products are. Reactants higher, products lower, that has to be exothermic. All right. There's a series of 5 arrows here, A, B, C, D, E. We're trying to identify each one of these symbols with a certain arrow. So the energy of the reactants, here's our reactants, the energy of our reactants is arrow A. The energy of our products, here's our products. E represents the energy of our products. The delta H is always going to be the energy of the difference between the energy of the products and the energy of the reactants. Okay, so find where your HP is, that's here, this line right here, and the energy of your reactants is here. So the arrow that shows you the difference between those two lines is D. The activation energy, remember, is the energy you have to add to the reactants up to the peak. So if the reactants are here and the peak is here, the arrow that goes there is B. All right, let's take a look at the bottom graph. Right, this is an endothermic graph. We've got reactants here, products here. Products are higher, so that's an endothermic process. The arrow that represents the energy of our reactants is D. Now the energy of our products, be careful here. You might want to say A, but the energy of our products is actually A plus D, right? Really, it's this entire arrow here, but there is no arrow that goes that whole distance. So we're going to have to say A plus D. The difference in the energy of the reactants and products, right? Delta H is HP minus HR. So the difference between the products and the reactants energy is arrow A. And lastly, the activation energy, which remember is the energy you add to the reactants. If the reactants are here, the activation energy goes all the way to the top. The only arrow that covers all that distance is C, or I suppose you could say A plus B. That would also do it, but the easiest answer there is C. All right, so in this video lesson, we have looked at potential energy diagrams for both endothermic and exothermic reactions. We've identified the energy of the reactants and the energy of the products, the difference of which is the delta H of the reaction. We've also added into this how to graph activation energy, which is always going to be a point higher than the energy of the reactants. All right, that's it for this video lesson. We'll see you back in the classroom.